In this video, we are going to discuss Bernoulli's theorem. Or Bernoulli's theorem is actually the energy that is concerned in a flowing fluid. As we have already discussed about fluid dynamics introduction. See, when a fluid is flowing, for example, let's consider a cross section. Let's consider a streamline. Let's consider a streamline. There is an orderly flow of a fluid from one point to say another point. Okay, and these dotted lines are again streamlines. And let us assume we have considered two areas. Here let it be having an area A1, having a pressure P1, and the liquid is flowing from this side. That means you are going to give some energy from this side so that the fluid is flowing this side. When you are giving some energy, you are pushing some energy from this side, or if you are giving some pressure energy, you are going to give from this side. The fluid starts flowing and it is going to some other region. So here we have considered two regions, and let the height from the surface be h1 here. Similarly, we are going to consider another region having area A2, pressure V2, velocity of flowing fluid, that is V2, and h height from the ground to this surface, it is h2. Okay, so we have told that this is a streamline and there is an orderly flow. So whenever you are giving some energy, there is a force. You are giving some energy from this side. So there is a force, and due to this force, what happens? Some amount of pressure is built up, and due to that, the fluid or the liquid starts flowing. Okay, now let us see. So the theorem states that total energy of small amount of incompressible liquid. So some of the keywords that is usually used is incompressible, mobile, which is capable of moving. Incompressible liquid that is flowing from one point into another without friction remains constant throughout the displacement. Or the theorem states that the pressure energy plus kinetic energy plus potential energy is a constant. Okay, this, even though we discussed in our fluid dynamics, we'll discuss. So, and also when this is for a unit mass, the theorem is expressed as P by rho plus half V square plus H rho is equal to a constant. So these two are the statements for the Bernoulli's equation. Now we have to prove. For that proof, we are going to consider this tube, and between two transverse sections, one is here, let it be X and let it be Y. One is at the section X and another is at the section Y. And we are saying we are having the pressure, velocity and cross-sectional area be P1, V1 and A1. Pressure, cross-sectional area and the velocity be P1, A1 and V1, which is at a height h1 from the ground. Another transverse section we have considered here is Y, having an area of cross-section A2, pressure P2 and the velocity of the fluid is V2 at a distance or height h2 from the ground. Okay. Now we are saying about the steady flow of small amount of a liquid. Say let it have a mass m. Let it have a mass m. Okay, and we are saying that this liquid flows from this section, that is at the section X, and simultaneously it is moving or it is exiting from the same amount of mass of liquid through this section Y. So same amount of liquid that is entering here in this cross section, say X, will be leaving through this cross section, say Y. And we have considered m is the mass of the liquid. Okay, let us see that let the mass of the liquid be flowing through this area A1, and let it move through a small time, say delta t. And if it is moving at a distance, say v1 delta t, we know velocity is equal to distance or displacement by time. So here it is delta t and the distance moved is velocity into time. So when it is moving from this area, through this area, the distance is v1 into delta t, and this is parallel to the axis of the tube. See, everything is parallel to the axis of the tube. But this flow of liquid is along the direction of the force. What is the force? We know pressure is equal to force per unit area. So force is equal to pressure into area. Okay, so that force will be here, the force acting will be equal to area into P1. Okay, this force will be acting over this area A1. അപ്പോൾ A1 എന്ന് പറയുന്ന ഏരിയയിൽ ആക്ട് ചെയ്യുന്ന ഫോഴ്സ് എന്താണ്? A1 into P1, that is pressure into A1, that is area of this region, that is the force acting here. Okay, now we know that work done is equal to force into displacement. Force into displacement or distance. So we can calculate W1 is equal to A1 force into displacement, A1 P1 into V1 delta T. This is force and this is the distance or the displacement. Okay, similarly at the section Q, the letter that is leaving, the amount of fluid or mass of the fluid that is entering through X will be leaving, the same mass will be leaving here. It will be having a work done as A2 P2 into V2 delta T. Okay, so the net amount of work done by the pressure, what will be? It will be W is equal to W1 minus W2, that is A1 P1 V1 delta T minus A2 P2 V2 delta T. Delta T being common, it has been taken outside. Okay, so this is what we say about the net amount of work done by the pressure forces during the time delta T on the system. Okay, now we shall once again start with our pressure energy, potential energy and kinetic energy. We will take in general as P and then we will start writing with these variables. Okay, so now let us first consider about the pressure energy. We are going to say in general now. Okay, pressure energy. So energy, so we have, I will write the formulas once again. We have energy is equal to work done on the fluid, right? And we have taken work done is equal to force into distance or displacement, and force we know that is pressure into area, this is length. So energy is equal to pressure into volume. That is what we have written now here. Okay, now let this be here. Now let us see what is the energy due to pressure in the fluid. That is energy due to pressure in the fluid is given by P into V. Okay, P into V. Energy is equal to P into V. Now we are going to consider the energy of the fluid per unit volume. That is pressure energy per unit volume, that is equal to PV by V, and we are getting it as P. So that is pressure energy per unit volume. Similarly, let us write for pressure energy per unit mass, that is PV by mass. We know what is, this is P by rho. We know density is equal to mass by volume. So volume by mass means density. Okay, so using that we have written pressure energy per unit volume as P and pressure energy per unit mass as P by rho. Similarly, let us see about kinetic energy. Okay, kinetic energy in the fluid is, as we know, kinetic energy in the fluid is represented as half mv square. Okay, now let us write for kinetic energy per unit volume is equal to half mv square by volume v. This is volume. We know again mass by volume is density, so we can write it as half rho v square. Again kinetic energy per unit mass, that is half mv square by m, or we get it as half v square. Okay, this is velocity. Now similarly we are going to write potential energy in the fluid. We know at a certain height potential energy is given by mgh. Again potential energy per unit volume, that is mgh by volume. Again mass by volume, we get it as density. Again potential energy per unit mass, mgh by m, and we are getting it as gh. Okay, so see what happens. We told that whenever we are giving here pressure energy, what happens? The fluid, or whenever you are giving energy, there is a force that is building up in this particular area. ഒരു എനർജി കൊടുക്കുമ്പോൾ ഇവിടെ എന്താവും, ഈ പർട്ടിക്കുലർ ഏരിയയിൽ ഒരു ഫോഴ്സ് ബിൽഡപ്പ് ചെയ്യും. ദാറ്റ് ഈസ് വാട്ട് വി കോൾ പ്രഷർ. And due to this pressure energy, what happens? The fluid or the liquid starts flowing from the lower height. See, this is height h1 is lower compared with that of h2. So from the lower height, the liquid starts flowing to the higher height. That means the pressure energy here is getting converted to kinetic energy and potential energy. So how much pressure energy is consumed here? എത്ര പ്രഷർ എനർജിയാണ് ഇവിടെ ഉപയോഗം വന്നത്? എന്തിനാണ്? അതിന് കൈനറ്റിക് എനർജിയിലും പൊട്ടൻഷ്യൽ എനർജിയിലോട്ട് മാറാൻ വേണ്ടി ഹൗ മച്ച് എനർജി, പ്രഷർ എനർജി ഈസ് കൺസ്യൂംഡ് ഹിയർ. ദാറ്റ് ഈസ് വാട്ട് വി ഗെറ്റ് ഫ്രം ബെർണോളിസ് തിയറം. ഓക്കെ, നമ്മൾ സോ വാട്ട് വി ആർ ഗോയിങ് ടു ഡു, ലെറ്റ്സ് സീ. സോ ലെറ്റ് us റൈറ്റ് ദ പ്രഷർ എനർജി per unit mass is equal to P1 by rho minus P2 by rho. Okay, or you can also write P1 minus P2 by rho. Okay, because we have already written and we have kept for pressure energy unit mass, we have written P by rho. So this equation we are going to write it for the two areas now. So now this energy is used to raise the kinetic energy and potential energy. See, the speed of the fluid is increasing. The speed of the fluid is increasing and it is going from a lower height to higher height. That means kinetic energy is increasing as usual. Potential energy is also increasing. Now, what is the energy used as kinetic energy? Kinetic energy per unit mass is equal to, already we have written here, that is half v square. So for the two areas we are writing it as half v2 square minus half v1 square. That is actually gain of energy, right? Now next we are going to write potential energy per unit mass. That also we have written and kept here gh. That is, we are going to write it for two heights, that is g into h2 minus h1. Okay, so we have written for that also. Now we have told that whatever pressure energy we have given, whatever energy given is equivalent to, we told that we are having this area, whatever mass of fluid is entering here, that same mass will be leaving here. That means energy given to started for flowing, that will be equal to the energy that is taken. That is according to our conservation law. That is according to law of conservation. According to law of conservation, we can write 1 by rho P1 minus P2 is equal to half kinetic energy per unit mass into potential energy per sum of kinetic energy per unit mass and potential energy per unit mass. Now we can write it as P1 by rho minus P2 by rho is equal to half V2 square minus half V1 square plus GH2 minus GH1. Now we are going to rearrange in such a way that the area in entering, the mass of the fluid entering here, we will write together, and mass of the fluid that is leaving here, we will write it separately and we will equate them, because whatever mass is entering here, the same mass is taken outside. So we can write it as P1 by rho, this we will be taking this side, half V1 square, this term we will be taking this side, that is equal to, this term we will be taking that side, RHS, plus GH2. Or we can say that during a streamline or orderly flow, sum of all the energy at all cross section remains constant. And this was the first statement here, as we already told. Pressure energy plus kinetic energy plus potential energy. This is the pressure energy, this is kinetic energy, and this is the potential energy. It is always remaining to be a constant. This is actually what we learned from Bernoulli's theorem. Okay, and now we can say, see here we are having, so we can generally we can write P by rho plus half V square plus GH is equal to a constant C. This is the Bernoulli's theorem. So sum of three types of energy of a perfectly mobile, incompressible, streamline or orderly flow of a liquid is constant. When one type of energy decreases, the other type of energy will increase and vice versa. So that means the three forms of energy of a liquid are mutually convertible. The forms of energy can be convertible. Okay. Now we are going to divide it by G. We are going to divide this equation by G. That is P by GH plus half V square by G plus H is equal to a constant. And this P by rho G, sorry, this is rho, not H. P by rho G, this term is known as pressure head. Okay, and this term is known as velocity head, and this term is known as gravitational head. This is known as gravitational head because this is the height through which the liquid must fall freely to attain the velocity V. So that means that pressure head plus velocity head plus gravitational head is a constant. Or in other words, Bernoulli's theorem states that in all the points, the streamline flow of an incompressible mobile liquid, sum of the pressure head, velocity head and the gravitational head is a constant. See, if the liquid is flowing horizontally, what will happen? The gravitational head H is a constant. For a horizontal flow, the gravitational head is a constant. That means we will be having only these two terms. That is pressure head plus velocity head is a constant. That is P by 0 plus half V square by G is a constant. Or you can also write P by rho plus half V square is a constant. Now, if in a liquid, the flowing horizontally and the pressure and the volume P1, velocity be P1 and V1, and then there is another point having pressure P2 and V2, then we can write it as P1 by rho 1 plus half V1 square is equal to P2 by rho 2 plus half V2 square. So, this relation will tell us if you are having two liquids and G, okay. Now, or we will write it once again. That is, if you are having 2 points P1 by rho half V1 square and P2 by rho plus half V2 square. If you are having a relation, that is, if a liquid is flowing horizontally and the pressure and velocity at 2 points are given, if we can relate like this, this means that greater the velocity corresponds to lower pressure. Greater the velocity corresponds to lower pressure and vice versa. For example, when a liquid is flowing through a horizontal tube having a vent or a constriction, the velocity of the liquid will be considered to be increased and pressure will be decreased. And this is as we are applying in some instruments like Venturi meter or pitot tube or a construction of various exhaust jet pumps. That is, Bernoulli's theorem has many applications like in many of the applications we are using like in exhaust jet pumps and all used nowadays. Thank you.